The Big Bang is on the ropes. It's amazing. Professor Simon, I don't know if you've ever watched his YouTube channel, but he just released a video. The Big Bang Theory is wrong. It's amazing, and there's a convention that the Demystify Sci podcast is putting on in Portugal. I'm considering going to that. I don't know. I've got a bunch of animals and stuff, but I would like to go to that. There's going to be like a lot of the no big bangers are going to be there. I would love to have a conversation with them in a room. It's amazing because all you have to do is use gravitational redshift. It's literally the one stepping stone that you need to, and once you lay that stepping stone down, it takes you into an entirely new world. And I mean, it's very simple to do. It's very simple to do. In the past, I've used universal gravitational acceleration, but that didn't catch on. Nobody believed that. So this is my new method. This supersedes all the other stuff I've talked about. I have probably made some mistakes in the past, and I may even make mistakes here. Heck, I had the wrong equation when I first started this video, and I had to go through and I had c squared instead of r squared. But this is the Hubble constant. Now, if you don't know what the Hubble constant is, use Wikipedia. It's a distance proportional redshift in starlight. So it's what we're doing here is reinterpreting that redshift as gravitational redshift instead of the expanding universe, because the expanding universe is nonsense. It's dark energy is dark magic, and it's literally just gravitational redshift. So this 2.33 times 10 to the negative 18 hertz is this is kind of our method of measuring how much redshift there is. That equates to around 72 kilometers per second per megaparsec. That's if you reinterpret it as expansion. However, like I said, it's gravitational redshift. And so we can determine the mass. You can rearrange and solve for mass or rearrange and solve for density with these two equations on the left here. And this is just the Schwarzschild radius. It's amazing. C divided by 2.33 times 10 to the negative 18 hertz this is the Schwarzschild radius. This is also the observable limit. Now, there are several problems with mainstream cosmology. If you say that it's gravitational redshift, they will balk. The first thing they'll say is that there's not enough mass, and just that's nonsensical. It's like saying there's not enough dark energy. It's like we're reinterpreting whatever mass you want to say, and it's just gravitational redshift. It's caused by nested gravitational wells. Stars are inside galaxies. Galaxies are inside galaxy clusters. Galaxy clusters are inside superclusters. Cosmic filaments, walls, arcs, observable limit. I mean, what we define as objects are not objects. Okay, it's all a unified manifold. It's all one big giant nested gravitational well. Okay, that's what general relativity is. And so this equation does work. It does not matter what anybody else says. This does work. And the way it works is you use the null geodesics as reference lines for the radial coordinates and then assume spherical symmetry. That's why it works. It's because you have to have a logical way of mapping the manifold, and that is the best thing that you can have. The FLRW the FLRW has a preferred frame of reference. That's usually the other retort. The first retort that they say is that there's not enough mass, and then the next retort is, well, you're using a preferred reference frame. No, I'm not. I'm using the null geodesics. So the location of emission is always going to be the center of your metric. It's always going to be the center of your metric. We assume spherical symmetry. Birkhoff's theorem applies. We can use the Schwarzschild metric. We have a Schwarzschild radius, which is a coordinate singularity. It's like a mathematical artifact. It's not a true black hole, but it does occur around that 13 billion light years or whatever. This right here. This is the Schwarzschild radius, the observable limit. at this point, this is where it gets really interesting. We have stars at this point, and then we also have the vacuum, the black stuff. I'm talking about the black stuff here, okay? That's going to be where the Hawking radiation is emitted at the observable limit. Now, Hawking radiation equation, that's this equation right here. Hawking radiation is usually inversely, the temperature of the Hawking radiation is usually inversely proportional to the Schwarzschild radius, meaning that the larger the radius is, the lower the temperature. And that's the case with this one. We have an extremely low temperature for our universe, 1.4 times 10 to the negative 30 Kelvin. Okay? That's terrible because we need 2.7 degrees Kelvin. However, at 1 Planck length, literally 1 Planck length, well, there's a little bit of wiggle room there. I'll get to that in a second. But at 1 Planck length, we have enough gravitational blue shift in our case because now the center of the metric has no mass in it. Now the center of the metric is the vacuum. And at the vacuum, Birkhoff's theorem says it's basically like everything goes to the point of the observation. All of the mass goes to there. And so so now we have a gravitational blue shift for that. And it's just enough to get this 2.7 degrees Kelvin. Now, with 2.33, I get like 2.78 degrees Kelvin. And then at 2.33333, I get like 2.70 degrees Kelvin. And so it's a little finicky. It also depends on the calculator. The calculator has to be extremely precise or it's not going to work. Wolfram Alpha is amazingly precise, and it would work for this, except I run out of there's a character limit, and I would have to remove. You have to remove all the units, and then I think it says undefined when you remove the units. It doesn't work. But regardless, this is the equation you would use. Okay, another thing here. This is the Planck length equation. Like I just thought it was cool because I can take the Hubble constant and put it in here and derive the Planck length, h squared times the Schwarzschild radius cubed. I think that's right. Hopefully I didn't mess that equation up. But I mean, this is so incredible. Like, to me, this is the best thing you can ask for out of somebody. This literally resolves all the problems because the nonlinear nature of gravitational redshift, we don't have to worry about dark energy. With dark matter, this distribution profile right here, this resolves all of the dark matter problems. I think you need a scale factor or something, depending on what scale you're in. That's for another video, but I don't know. This is the problem I have. I don't know what to say. Like, it's literally just use gravitational redshift. It's just gravitational redshift. And everything falls in place. So, like, the retorts are easily addressed with this null geodesics. And then there's nothing else. It's over. Rewrite all of the science books. That's what we have to do. We have to convince everyone that this is it. And this is it. Like, this is the math. Like, this is amazing. I don't know how else to state it, though, like, except to just say that it's good, and if nobody else thinks it's good, then whatever. Anyways, you guys think it's great. Like, y'all have been here for a while. Me and my 500 subscribers, we know what's going on, and the rest of all the people I don't know what they're doing. Everybody's wanting to have their own theory. But it's just gravitational redshift. That resolves basically all of cosmology. You can keep going, though, because this occurs at 1 Planck length. We've now tied in quantum field theory with general relativity. And then, now, also, we have an inverse mass density. So a mass density is a variable once again, which means energy density in quantum field theory is inversely proportional to the radius. And guess what? We have a lower bound. We have this 1 Planck length. And an upper bound. We have the Schwarzschild radius. So now all of the ultraviolet problems are gone. So general relativity is compatible with quantum field theory. I don't know what else to say. Like, this is this should be published, but I guess maybe I'm just a crazy person. That's entirely possible. It's entirely possible because this stuff will make you crazy, especially when you do it. You spend so much time on it. You submit an article, it's immediately rejected. You make a tweet, no one sees it. You make a video, 15 people see it, and 2 people like it, and that's it. It's like, and then you go to a forum and you type it, you get banned. And it's like, okay, I don't know what else to do. This is it. I'll just do this till I die. Y'all have a great night.